Hi there. I wanted to go into a little bit more depth on the background of logarithms, why we use them, and why they're really important for acoustics and noise control, and maybe do one or two little examples of logarithms. So we're going to start from a pretty basic point here, just by talking about powers. So if I write something like 3 to the 4, 3 to the fourth power, well, um, we know that that's 3 times 3 times 3 times 3. So it's 4 times. Yeah. And okay, what is that? Let's just get that down to a number. Well, 3 times 3 is 9. 3 times other 3 is also 9. So that's 9 times 9, or 81. So 3 to the 4, 3 to the fourth power is equal to 81. Most folks are pretty comfortable with that. Let's say I had the 81 and I had the 4 and I wanted to get back to the 3. Like, what's the inverse of this process? So if I take 81 and I raise it to the 1 over 4, the 1/4 power, that's the same as writing the fourth root of 81, which is 3. And it's very important that it's not like 8 to the negative 4. Don't do that. That if you want to know what that actually is, that's 1 over 8 to the 4. But that's a totally different thing. You're not going to get to 3 that way. That's not what we want. So just ignore that for now. So we started off with 3 to the 4 equals 81. Then we had 81 to the 1/4 power equals 3. And then we might want to do a third thing that said, if I had the 3 and I had the 81, and I wanted to know what power do I need to raise the 3 to get to 81, that might be something we might want to ask. And we know from up here that question mark is 4, but this is what logs do for us. So they find a given power for a certain base. So this 3 is the base because it's sort of on the bottom of the exponential expression. So we would write this as log base 3 of 81 equals 4. Now I've seen this written in a certain way with triangles, and I think it's kind of fun. So if you have a triangle like this and said 3 to the 4 is equal to what? That's what we did up here. That's exponentiation. That's sort of a power. In the second example here, we had something to the 4 is equal to 81. So that's where we got roots or fractional powers. And then the logarithm is the missing triangle here, is where we know what's at the base. That's the 3, and we sort of know what the big number is, and we are missing this one. That's where logarithms come in. And so, okay, it's just this different mathematical operation. It's sort of not really good for anything until you can calculate it. Well, but calculators can calculate this, can do logs for you. But there's another thing that there's some properties of logs that are going to make this make a lot of things easier. So let's say we wanted to raise 3 to the 6th power now. So 3 times 3 times 3 times 3 times 3 times 3. And if you plug that into your calculator, which I did beforehand, is 729. So we can write 3 to the 6 as 729. We could do this business with logarithms. I'm going to do something else and say, let's just for fun group this group of 3's together and this group of 3's together. So you could write that that's 3 to the 6 is equal to 3 to the 4. There's 4 of them there. Times 3 to the second power, 3 squared. Okay, that's sure, we're just kind of having fun at this point, but one thing you might notice is, well, oh, there's these powers up here have an addition relationship. So like 6 is equal to 4 plus 2. So there's something related to the powers up here and addition down there. If you wanted to write that in terms of logs, 6 is equal to log base 3 of 729. Right? What did I need to raise the 3 to get to 729? I needed to raise it to the 6th power. 4 is log base 3 of 81. We did that up there. Plus 2 is log base 3 of 9. So you might get a sense for what logs are doing here and what they're good for. They're basically turning multiplication and exponentiation into addition. And so in general, it doesn't just happen to be true. In this case, this is true in general. So if we had, say, 3 to the a times 3 to the b, 2 different powers, you can also write that as 3 to the a plus b, add the powers together. And if you wanted to write this in terms of logs, the multiplications become additions. So you could say log base 3 of a plus log base 3 of b is equal to log base 3 of a times b. So we're sort of looking at the exponents up here, the powers. So, you know, it's a little bit useful for making some calculations go quicker, but in this day and age, calculations kind of go as fast as we need them to go, and it's fine. Where this is really going to be useful is when it comes to presenting results, doing some plotting, some graphs and things. So let's say I wanted to draw a number line with just with these numbers, 9, 81, and 729 on there. Just because I have some, I have some situation where I've measured 3 things, and one of them's 9 pounds, 81 pounds, and 729 pounds, and I want to put them on a graph. So okay, so I put the 9 there, and I start making more tick marks, and boy, I'm gonna kind of get bored before I get out to 81 might be all the way over here, and 729 is I don't have enough room on the paper for that. But if I wanted to draw the logarithms of those things, so let's call this x, and then let's draw log base 3 of x. Well, so the 9 is 3 squared, so 9 on here maps down to 1, 2, so that's 3 squared is equal to 9. Where does the 81 go? Well, the 81 is 3 to the 4th power, so 3 to the 4th is there, that's 81. And where does the 729 go? It used to be like 16 pages over, but now it's just, okay, 3 to the 6th is 729. And these are like nice and evenly spaced. That's kind of fun. So what the logarithm's doing for us is it's taking things that are spread way, way, way far apart that span lots of orders of magnitude and cram them down into a really small part of the graph. This happens to be extremely useful in acoustics because a lot of the sounds that we encounter in everyday life, some things are very, very, the loud things are many orders of magnitude bigger than the quietest things. So say like a gunshot and a whisper they're not like 100 units apart. They're a few, several million units apart. One of them's a million times bigger than the other, and we'll be talking about what those actual units are later on. So this sort of relationship where we take numbers that are hugely far apart and we cram them down into a nicer place to look at is what logs are good for. Let's talk about a couple other properties of logs here. Back to our example with the threes. Let's say 3 to the, what if I took that 3 to the 4, that 81, and I squared it, right? So 81 squared, now the numbers are getting quite big. So that's 6,561. But you can also write that, I'm not going to write it out here. So we'd have 3 times 3 times 3 times 3 times 3, 4 of those. I guess I will write it out. 3 times 3 times 3 times 3. And then squared, you just do that again. 3 times 3 times 3 times 3. The parentheses got a little sad here. So you can also write that as 3 to the 8th power. In terms of logarithms, you would write log base 3 of 81 equals 4. Again, log base 3 of 81 squared is the same as log base 3 of 3 to the 8th power. What power do you need to raise a 3 to get 3 to the 8th? Well, it's just the 8th power. This isn't magic. So if you have log base a of a to the p power, you just get p back from definition of log. So the point I was trying to make here is that when we did log base 3 of 81, we got 4. When we did log base 3 of 81 squared, we got 8. So you might notice we could have just multiplied this 2 out here. So you could say this is 2 times log base 3 of 81 is equal to 8. So you can kind of bring these powers down. A power inside the log becomes a multiplication out here. So now we're to the point where maybe we'll just start writing down some identities and definitions and things. So let's say we have log base b, just a generic thing of some number c, and the thing we got out of that is a. So this implies the relationship b to the a is equal to c. The thing we just showed is if you have a power in there, log base b of c to some power p, you can bring that out as a multiplication. P times log base b of c. Other identities would be something like if you multiply it by something else, we saw that a little bit ago, c times d. So the log of the multiplication, log of the product, is equal to the sum of the logs, log of c plus log base b of d. And the bases are all staying the same throughout this whole thing. And you might guess what happens if you divide two things, c divided by d. This addition turns into a subtraction, log base b of c minus log base b of d. There's one thing that actually doesn't come up all that much, is like what happens if you don't need something base b, and you need something, base 7 or something. if you have log, let's see, let's just make something up. Log base 7 of 13. This is an identity. I won't prove it to you. You can do log base whatever of 13 and divide by log of that same thing of 7. So if your calculator doesn't have a log base 7 button on it, you can just do something like, they almost always have a log base 10. You can do log base 10 of 13 and divide by log base 10 of 7, and you're good to go. So let me just go through one or two little algebra operations that happen all the time with logarithms before I go here. So one thing we have to do in acoustics quite a lot, and we'll explain what these numbers are later, but what the symbols are. So if you have some L is equal to 10 times log base 10 of, say, P, and what you want to do is solve for P. You have L, you want to solve for P. So we just need to do this whole process backwards. Log base 10 comes up a whole lot in acoustics. It's the basis of decibels. We'll get to that later. So we are just doing some algebra, do the same thing to both sides. We're going to divide by 10, so L over 10 is equal to log base 10 of P. The undoing a logarithm means you raise both sides of the equation to the same power. So what I'm going to do, we need to, the power of we raise the base, which is 10, both sides, so 10 to this side and 10 to that side. So L over 10 is equal to 10 to the log base 10 of P, which I just said is just equal to P. So when you're solving for P, you would just do 10 to the L over 10. That's one thing that happens a lot. Another thing is maybe sort of a compound interest type of problem. Let's say we have, I just use P, I'm going to use P again here, but a compound interest, if you have what's my money as a function of time, it's related to compound interest, my money at time 0 and e to the rate times time. This is a continuously compounding interest formula. You don't really need to know where it comes from, but this using e, 2.7 whatever, as e to the some kind of power. This happens all the time in noise control, actually, and not just in the context of interest. So maybe you said, okay, what if my rate is I don't know, 7%, 7% per year. So let's say this is per year, and I want to know how long it takes to double my money. So I would say I want P over my current money over my starting money to be 2, so I've doubled my money. So that's equal to e to the RT. I want to solve for t. So what I do is I take a logarithm of both sides of this equation, and I need to make the logarithm match the base. So in this case, the e of the thing I want to get rid of. So I would do log base e of 2 is equal to log base e of e to the r times t, and these things kind of cancel, so I just get r times t. And you may know, you may maybe search the back of your the cobwebs in your brain here, but log base e is frequently written as ln. That's the natural log. So natural log of 2 is equal to r, which is my my rate times time, or 0.07 times time. So the time it takes to double my money in this case is I grab my calculator and figure out what log 2 is, then divide by 0.07. Log 2 happens to be 0.693. Log base E, natural log of 2, something like that. So this is, you know, close to, I don't know, close to 10 years at a 7% interest rate. So something, you know, a little bit practical for you. All right, that's all I have on logarithms. Please let me know if there are more questions or I can provide some more examples. Thanks.